Okay, dear friends, so we will analog integrated circuit in the first module, third lecture. Okay, today we are going to see operational amplifiers. Operational amplifier, op-amp, it is a direct coupled very high gain differential amplifier or amplifier which consists of one or more differential amplifiers followed by a level translator and an output stage. So it is available as a single integrated circuit package which has inverting input terminal, minus terminal or plus terminal, non-inverting input terminal and an output terminal. Some examples of op-amp ICs are EC204-AIC, MC1530, etc. In our class also I have given several types of dual inline package op-amp ICs. Now here the operational amplifier, these are some ideal characteristics of an op-amp. Already we studied Openloop voltage gain is infinite, then input resistance is infinite, then output resistance are not equal to 0, bandwidth infinite, 0 offset, then V not equal to 0 when V1 equal to V2 equal to 0, that is 0 offset. Then ideal op-amp draws no current at input terminal, so the both terminal currents are 0. Output voltage is independent of current drawn from the circuit. Then CMRR is infinite and the slew rate is infinite. These are the ideal characteristics of op-amp. Now equivalent circuit of op-amp. Now we have negative input terminal, that is called inverting input terminal, then positive input terminal and output terminal. These are the outside physically we can view the terminals. Now the internally we have, there are two types of model. One is ideal op-amp model and practical op-amp model. Second one is practical op-amp model. In the ideal op-amp model we have only the equivalent diagram. In that circuit symbol, inside that we have A into the differential voltage or the difference between two terminal voltage VD. So that is the output. Now in practical case we have some input resistance and output resistance. So the differential input resistance R suffix D and also the output resistance R suffix 0. This R is a small letter R that represents the AC input resistance and output resistance. So this is the equivalent diagram. So the final output V naught equal to A into VD. So VD is the difference between terminal, positive terminal and negative terminal voltages. A is called open loop gain. Now here we have a voltage transfer curve of operational amplifier or op-amp. We know the transfer curve means the input and output voltage graph. So here we have, this is the voltage transfer curve of op-amp. Now here the plot of output voltage V naught against the differential input voltage VD when the voltage gain is constant. Now the output voltage cannot exceed the positive and negative saturation voltages. These saturation voltages are specified for a given values of supply voltages. For example, if we are applying a supply voltage of plus 15 volt, now the saturation voltage of 741 typical value is plus or minus 13. So positive saturation is plus 13, negative saturation is minus 13. That is, the output voltage is proportional to the input difference voltage only until it reaches the saturation voltages, and thereafter the output voltage remains constant. So this curve is called an ideal voltage transfer curve because output offset voltage is assumed to be 0 here. So this is the ideal voltage transfer curve is shown in the slide. Now if the curve is drawn to scale, the curve would be almost vertical because of very large values of AD, because the differential gain of op-amp is very high. Okay, if you take the scale, so it is almost vertical because of very large values of AD. Now here open loop op-amp configurations. In this case or in the case of amplifiers, the term open loop That means that no connection of any type exists between input and output terminal. That is, the output signal is not fed back in any form as part of input signal. That is called open loop configuration. In the open loop configurations, the op-amp functions as a high gain amplifier. There are three open loop op-amp circuits are generally here. The first one is the differential amplifier, and the second one is the inverting amplifier, and the third one is the non-inverting amplifier. Now the open loop differential amplifier, the source resistance R in1 and R in2 are normally negligible compared to the input resistance of op-amp, practical op-amp Ri. Now here we have two input voltages applied, V in1 and V in2. The output voltage is equal to AD into V in1 minus V in2. So the voltage drop across these resistances can be assumed to be 0. So V0 equal to AD into V in1 minus V in2. Now the open loop configuration inverting amplifier. Now here the input is applied to the inverting terminal and the non-inverting terminal is grounded. So here V0 equal to minus AD into output voltage V0 equal to minus AD into input voltage Vin. The negative sign indicates that the output voltage is out of phase with respect to input by 180 degree, that is of opposite polarity. It is called inverting amplifier. Now the next is the open loop non-inverting amplifier. Now in this configuration, the input voltage is applied to the non-inverting terminal and the inverting terminal is grounded. So here the output voltage and input voltages are same phase. So the output voltage V0 equal to AD into Vin. There is no phase reversal at the output. Now open loop op-amp configurations, any input signal slightly greater in magnitude than 0 will drive the output to saturation level because of the very high value of open loop gain. This is very important statement. That is, because of very high gain of open loop gain, in open loop configurations, any input signal slightly greater in magnitude than 0 that will drive the output to saturation levels. So the second point, thus when operated in open loop, the output of the op-amp is either negative or positive saturation, or it switches between the positive and negative saturation levels. So therefore open loop configurations are not used in linear applications. So you please note that why the open loop configurations are not used in linear application. The answer is given in the first 2 points. You please note. Okay. Now this is the block diagram of an op-amp. Repeatedly, Kerala Technological University AIC analog and integrated circuit question paper is having the same question, that is, describe the stages of op-amp or describe the block diagram of op-amp or different levels of stages of op-amp. Now here we have 4 stages. The input stage, here we have 2 inputs, non-inverting input and inverting input. Then the intermediate stage, level shifting stage and output stage. The operational amplifier is a direct coupled very high gain amplifier consisting of one or more differential amplifiers followed by a level translator and an output stage. The input and intermediate stages are dual input. In the input stage is a dual input balanced output differential amplifier which provides most of the voltage gain of the amplifier and also establishes the input resistance of the op-amp. The intermediate stage of op-amp is another differential amplifier driven by the output of the first stage. Okay. Now this is usually dual input unbalanced output differential amplifier. The second stage, intermediate stage, containing a dual input unbalanced output differential amplifier. Now the third level, that is a level translator stage. So because of the direct coupling, the DC level at the emitter rises from stage to stage. This increase in DC level tends to shift the operating point of the succeeding stages and therefore limits the output voltage swing and may even distort the output signal. So we need to shift the Q voltage of one stage before applying it to the next stage. To shift the To shift the output DC level to 0, level translator circuits are used. The level shifter also acts as a buffer to isolate the high gain stages from the output stage. So this is the circuit of a level translator stage. Normally an emitter follower is the simplest form of level translator. The amount of shift obtained using simple emitter follower level shifter is V0 minus Vi, that's equal to minus VB minus 0.7 volt. If this shift is insufficient, use an emitter follower with a voltage divider. So here V0 minus Vi, that's equal to minus VBE plus I into R1. So there is some disadvantage, that is the signal voltage also gets attenuated by R2 by R1 plus R2. So here we have the circuit, that is if the shift is insufficient, we are using a voltage divider, so there is having some disadvantage, that is the disadvantage is the signal voltage also gets attenuated by R2 divided by R1 plus R2. Now the level translator stage, this AC attenuation can be avoided by replacing R2 with a current mirror. This circuit is also important. The question may ask how to avoid the AC attenuation at the level translator stage. That is, we can replace R2 with a current mirror, we can avoid AC attenuation. Now the output stage, which provides the amplifier with a low output resistance. The output stage should be able to supply relatively large load currents without dissipating a large amount of power. Now here the emitter follower class A output stage needs large power. Now the class B output stage to reduce power dissipation but turn the transistors on only when the input signal is applied. For this we use an NPN transistor and PNP transistor which are biased at 0 DC current. So class B output stage is here. That is, class B output stage is an emitter follower with complementary transistors. Now class B operation, here when Vi is positive, the input voltage is positive, Qn, the upper transistor Qn is on and supplies current to RL, and QP is off. At the same time bottom transistor is off. When Vi is negative, the PNP transistor QP is on, that is the bottom transistor is on and supplies the current to RL. Same time the Qn is off. So efficient in terms of power. This class B output stage is efficient in terms of power. Now here, but class B has a crossover distortion at its output. That is, for when Vi less than 0.5 volt, both the transistors are off. So this is shown in graph. The limitation of class B output stage is crossover until Vi exceeds VBE cut-in, that's equal to 0.6 or 0.7 volt. Now here we have the another option is the class AB output stage. Crossover distortion can be reduced by biasing the transistors at low current. In order to ensure that Qn and QP will remain conducting when Vi is small. This is called a class AB output stage. As Vi increases, one transistor conducts more while the other shut off. This is achieved by applying a bias voltage V slightly greater than VBE cut-in, that is equal to 1 volt between the two bases. Now here it is shown in the figure. Here we applied a bias voltage V. The small emitter resistances stabilizes the circuit. Now here we have the 741 op-amp circuit output stage. A simple way for biasing the class AB stage transistors using two diodes connected transistors as shown below. Now here this is the class AB output stage example of 741 op-amp circuit. The circuit is here. Now here we have the 741 op-amp circuit. This is the symbol inverting amplifier, non-inverting amplifier output terminal. Then a positive supply voltage plus VCC, that is the 7th pin. Then a 4th pin, that is a negative supply voltage minus VEE. Now here we have 741 is A BJT op-amp has large number of transistors, relatively few resistors, and only one capacitor. Requires two power supply plus VCC and minus VE. Typically we use VCC equal to VE equal to plus 15 volt, that is plus or minus 15 volt. No circuit node is connected to ground. Now this is the pin diagram. Now in this pin diagram it is very clear that it is showing that here we have 8 pin dual inline package. Now the first pin is offset null, the second one is in our inverting input terminal, and the third pin is our non-inverting input terminal or plus terminal. Now the fourth pin, that is our negative power supply voltage minus VE. Then fifth pin is our offset null. Then sixth pin is our output. Then seventh pin is our positive power supply plus VCC. Then eighth pin is not connection, is having no connection. Now this is the op-amp circuit, 741 op-amp circuit here, which is showing that there are the 4 stages. First stage is a dual input balanced output differential amplifier. Second stage is a dual input unbalanced output differential amplifier. Then an emitter followed level translator. Then an output stage A, class AB amplifier. This is the different stages. It is shown here. The input stage, intermediate stage or second stage, then output stage, then we have a input bias and level shifter stage. Okay. Now the frequency response of op-amp. Ideal op-amp have infinite bandwidth. Practically the op-amp, the open loop gain rolls at a higher frequencies. So the capacitive components in high frequency equivalent model, due to the capacitive components in high frequency equivalent model, practically the open loop gain rolls of a higher frequency. The higher frequency model of op-amp with a single break frequency, it is shown in our diagram. This is the high frequency practical model of op-amp. Frequency response of op-amp. Now here we have the frequency response, magnitude of voltage gain and the phase angle of voltage gain. It is shown here. This is the frequency response of op-amp. Now the frequency response of op-amp in S domain, which is given A is equal to A naught L omega 1 by S plus omega 1. Now here we are taking the break frequencies F1, F2 and F3. This is the gain equation. Then the frequency response, here we have 3 different frequency slopes. Now here we have the frequency approximation of open loop gain versus frequency curve. Now here the from 0 to F1, here we have the flat response. Then F1 to F2 there is minus 20 dB per decade slope. F2 to F3 we have minus 40 dB per decade. Then F3 more than F3, that is from F3 onwards minus 60 dB per decade. So each RC pole pair introduces a lagging phase maximum up to minus 90 degree. Then stability of op-amp. The op-amp are rarely used in open loop configuration due to high gain. Consider an op-amp with a resistive feedback. For negative feedback, the closed loop volt transfer function is A by 1 plus A beta, that is the closed loop transfer function, where A is the open loop gain, beta is the feedback ratio. When loop gain minus A beta equal to 1, we can get the sustained oscillation. So it become unstable. Okay. Conditions for sustained oscillations are Burgaussian criteria. We know that a magnitude of A beta equal to 1, then angle of A beta minus A beta equal to 0, that is the phase shift around the loop. Total phase shift must be either 0 degree or 360 degree. This is the angle condition. Now the stability of op-amp. Here we have, when used in inverting mode, the op-amp provides a phase shift of 180 degree at lower frequency. At a higher frequencies, due to each corner frequency, additional phase shift of minus 90 degree can take place. That is, for 2 corner frequencies, maximum phase shift equal to minus 180 degree. So at some value of beta at high frequencies, it is possible that magnitude of A beta equal to 1. When A has additional phase shift of 180 degree, which makes total phase shift 0 degree oscillations, that is verge of instability. Now the stability of op-amp is guaranteed if at the frequency for which the phase angle of A beta is 180 degree. That is, if the magnitude A beta is less than unity, the amount by which it is less than unity expressed in decibels is the gain margin. Alternatively, the amplifier is stable if at the frequency at which A beta equal to magnitude of A beta equal to 1, the phase angle is less than 180 degree. The difference is called phase margin. Okay, this is the graph showing the stability of closed loop op amp. Now gain in dB, the first it is showing the effect of feedback on open loop gain versus frequency curve. Now here we have 1 kep to 1 m. Okay, here we have a flat response that showing the open loop gain, and the second point A showing the curve for closed loop gain, then some dB, then curve for closed loop gain 60 dB, then 40 dB, then 20 dB as shown in here. So here we have for stable operation, the rate of closure between the closed loop gain projection and open loop curve should not exceed minus 20 dB per decade. Now the gain bandwidth product. The gain bandwidth product is the bandwidth of the op amp when the open loop gain is reduced to 1. That is called unity gain bandwidth. In other words, the product of the amplifier midband gain and the amplifier bandwidth is equal to gain bandwidth product. The gain bandwidth product for an op amp is nearly independent of the gain at which it is measured. That is, if we want to increase the bandwidth, we must decrease the closed loop gain. Now here the graph showing the gain bandwidth product. Now here that is the bandwidth at which the gain reduces to 1. Okay, thank you. എന്തെങ്കിലും ഡൗട്ട്സ് ഉണ്ടെങ്കിൽ ചോദിക്കാം. നിങ്ങൾ ഈ ലെക്ചർ നിർബന്ധമായിട്ട് കേൾക്കണം, നിങ്ങളുടെ നോട്ട് റെഫർ ചെയ്യണം. ഒന്നുകൂടി ഓർമ്മിപ്പിക്കുകയാണ്, നിങ്ങൾ ക്ലാസ്സിൽ നല്ല റിട്ടേൺ നോട്ട്സ് തന്നിട്ടുണ്ട്. ആ നോട്ട് നിങ്ങൾ റെഫർ ചെയ്യുക, എൻ്റെ ക്ലാസ്സും കേൾക്കുക. ഞാൻ ഇതിൻ്റെ കൂടെ PDF അയക്കുന്നുണ്ട്, അതും നിങ്ങൾക്ക് റെഫർ ചെയ്യാം. ഓക്കെ, ഇതിൻ്റെ കൂടെ തന്നെ പഠിച്ചു വരണം. നമ്മൾ ഇന്നത്തോടു കൂടി നമ്മൾ ഫസ്റ്റ് മോഡ്യൂൾ തീർക്കും. നാളെ സെക്കൻഡ് മോഡ്യൂൾ റിവിഷൻ കഴിഞ്ഞാൽ നമ്മൾ തേർഡ് മോഡ്യൂൾ ആൾറെഡി നമ്മൾ ഒരു പ്രാവശ്യം എടുത്തിട്ടുണ്ട്. ഓക്കെ, ഫോർത്ത് മോഡ്യൂൾ നമുക്ക് സ്റ്റാർട്ട് ചെയ്യാം. ഓക്കെ, താങ്ക് യു.